In this tutorial, we will be discussing the nature of light. In doing so, we'll be discussing the quantum mechanical model. This model explains the strange behavior of electrons. It describes electrons as they exist within atoms, and they also describe how those electrons determine chemical and physical properties of elements. According to Heisenberg, light and matter are both single entities, and the apparent duality arises in the limitations of our language. Matter has both particulate behaviors and characteristics. It has mass and it occupies space, and energy-like behaviors, like light, and characteristics. Most subatomic particles, such as an electron, behave as particles and obey the physics of light waves. This behavior is more prevalent due to the size of the particles. All matters possess this dual personality. The concept that describes the dual nature of matter, i.e. particulate and energy behaviors, is known as wave duality. The theory that describes the electron's behaviors is quantum mechanics. If we look at this graph here, we note the wavelength and the amplitude. The wavelength is from peak to peak, or similar point to similar point. If it has a longer wavelength, it's going to have a lower frequency, meaning it's going to take longer to go through one specific point. A frequency is how many times the peak of the wave will pass a specific part. So if I was measuring it right here, how many times that wave would pass in 1 second. So if it's a longer wavelength, it's going to have fewer times it's going to pass. Whereas if it had a really short wavelength, it will pass several more times. Therefore, wavelength and frequency have an inverse relationship. Light, electromagnetic radiation, waves have a frequency. This funny looking symbol here that looks like a V is actually the Greek letter nu, and it stands for frequency. The units are per second, so it's 1 over seconds, or a second to the minus 1, and that's what I was referring to in this graph. The distance between light waves is referred to the wavelength. Wavelength is given by the Greek letter lambda. Looks like an upside down Y. Lambda units are given in meters. It's important that you have it in meters and seconds and not nanometers or milliseconds or some other variation because of this variable right there. The formula is nu is equal to c over lambda. While c is the velocity of light, and that never changes. It's constant. 3 times 10 to the 8th meters per second. Because this is in meters and seconds, we need to make sure that the nu, the frequency, is also per second, and the lambda is also in meters. Let's have an example. Red light has a frequency of 700 nanometers. Notice nanometers. We need to get red of that. So 700 nanometers over 1. You might remember that nano means 9. So 1 times 10 to the 9th nanometers is equal to 1 meter. That comes out to be 7.00 times 10 to the negative 7 meters. So what would the frequency be? Nu is equal to c over lambda. So nu is equal to 3 times 10 to the 8th meters per second, while the distance is 7, the lambda is 7.00 times 10 to the negative 7 meters. The meters then cancel out to give us per second at the end. That final answer is 4.29 times 10 to the 14th seconds to the minus 1, or 1 over seconds. White light decomposes into constituent colors. Notice as it's going through the prism here, it's going in as white, and then it diffracts and it separates into its colors. Each have their own wavelength. but when they're all combined, they're white. This is the electromagnetic spectrum. It's a chart that illustrates the range of electromagnetic radiation. The classification of electromagnetic radiation is based on the wavelength. So here's frequency, here's wavelength. It's typically based on wavelength, but it could be both because they are proportionate. Notice as the wavelength gets smaller, the frequency gets bigger. Short wavelength, high frequency light has high energy. So here's the shortest wavelength and the highest frequency. Gamma ray falls under that category. Radio is the opposite. It's down here. It has the shortest frequency, smallest frequency, and the longest wavelength. High energy electromagnetic radiation can be potentially damage biological molecules. Notice X-rays are right here, and you may recall if you've ever had an X-ray, you've had to wear a shield to protect yourself. And then ultraviolet radiation is the issue with the sun and why you need to wear sunscreen. And this is called ionizing radiation. Visible light comprises only a small fraction of all the wavelengths of the electromagnetic spectrum. So what is color? All electromagnetic radiation actually has color. However, humans can only see a small amount of it. So it's only visible by color by a little bit. The color of light can be determined by either its wavelength or frequency. The visible spectrum, which is what we were just looking at, the electromagnetic radiation, the ones that breaks down into the colors. The white light is a mixture of all the colors of visible light from 700 to 400 nanometers. And it breaks down to red, orange, yellow, green, blue, purple. You might be able to remember this by Roy G. Biv. Sometimes people add indigo between blue and violet. Pretty much if you remember what a rainbow looks like, you can pretty much remember the order. Color happens when an object absorbs some of the wavelengths of the white light while reflecting the others. The observed color is predominantly the colors that are reflected. So let's talk about color and intensity. Color, the electromagnetic radiation, is determined by the wavelength, by the distance of the wavelength. So for the longer wavelength, it's going to have a shorter frequency. And you'll notice orange, yellow, blue. So when we're looking up here, 700 nanometers would be the red, down to 400 nanometers, which would be the violet, which is smaller. The intensity of the light is dictated by the wavelength's amplitude. So the higher that peak is, that's the amplitude. The higher the peak is, the brighter it's going to be. Now when they combine, when you have lights overlap, if it's in phase, that means that the peaks are at the exact same point on the waves. That's going to be constructive interference, and it reinforces the amplitude and just makes it larger. Destructive interference is when it's out of phase. Notice that the peak is here and the peak is here. And the trough is here and the trough is here. So they end up canceling each other out. So wave behavior of light, of electrons, is diffraction. Here's the wave crest as it's going by. Then it passes its point and it starts to diffract. This is a small opening, a small gap. Diffraction is the ending of light wave. Occurs when a light wave encounters an obstacle or travels through a slit similar to the size of its wavelength, and it starts to curve. Particles, however, do not experience it. If it gets to the point where it hits the barrier, rather than diffracting, it's just going to stop. Finally, if we have two slits where the light's traveling through, these light waves can now interfere with each other, whether it's destructive or constructive. If it's destructive, they're going to overlap and turn dark. If it's constructive, it's going to get brighter in those areas. So it all depends on how those wavelengths are overlapping each other. And this was the beginning of the nature of light.